Welcome to this explainer. If you think organic chemistry is just a bunch of abstract equations scrawled on a whiteboard somewhere, prepare to see it in a completely new light. Today, we're exploring the foundational principles of organic chemistry, but specifically geared toward fisheries. We're going to see how mastering this molecular language is actually the hidden key to understanding life, death, and toxicity in our aquatic systems. I mean, it sounds like pure science fiction, right? How does a tiny shift in a single electron's orbit determine if an entire marine ecosystem thrives or dies? But by the end of our time together today, you'll see exactly how these invisible atomic-level mechanics connect directly to the fate of our oceans, literally dictating everything from the survival of a single crustacean all the way up to apex predators. So here is our roadmap for today. First up, the rules of the lab. Then, we'll see this scientific method in action, followed by a deep dive into the quantum realm, and finally, we'll wrap up with how periodic trends drive marine toxicity. Okay, let's jump right into part one, the rules of the lab, handling hazards, and the SDS. Because before a marine chemist can go out and solve ecosystem crises, they actually have to survive the laboratory. And that starts with mandatory personal protective equipment, or PPE. But we aren't just saying throw on some gloves. We specifically require nitrile gloves. Why? Well, because standard latex gloves are completely permeable to many of the nonpolar organic solvents we constantly use in aquatic chemistry, like hexane. You also absolutely need ANSI-certified splash-proof goggles, a 100% cotton lab coat that extends below the knee, and closed-toe leather or rubber shoes. So yeah, no canvas sneakers, no mesh. Look, even with perfect PPE, accidents happen. Let's walk through the emergency acid spill protocol. If concentrated sulfuric or nitric acid splashes you, step 1 is immediately taking off that contaminated coat. Step 2, flush the skin with running water for a good 15 to 20 minutes. But here is where human intuition totally fails us. Do not apply neutralizing bases. It's a super common misconception that you should neutralize an acid with a base right on your skin. Actually, scratch that, it's a terrible idea. Doing so causes a rapid exothermic reaction, meaning it releases intense heat, and you will suffer severe thermal burns right on top of the chemical burn. Just use water, report it, and seek medical help. Waste disposal is another area that requires extreme precision because the stakes are incredibly high. Improperly incinerating halogenated organic waste, which are solvents containing elements like chlorine, think dichloromethane, can actually form toxic phosgene gas. Meanwhile, if an inexperienced student accidentally mixes non-halogenated waste, like toluene, with concentrated nitric acid in a closed waste carboy, well, it triggers a violent oxidation reaction generating nitrogen dioxide gas. That will literally cause a chemical fire and a massive explosion. Moving on to part 2, the scientific method in action, from observation to hypothesis. With lab safety lockdown, we can apply our investigative tools to real-world aquatic anomalies. Picture this. You observe sudden fish mortality in an aquaculture pond right after a heavy rain. A marine chemist takes that observation and frames it into a testable hypothesis grounded in chemical logic. The null hypothesis here assumes there's just no relationship, that rainfall doesn't alter the ratio of toxic unionized ammonia to the ammonium ion. But the alternative hypothesis proposes a specific mechanism. It suggests that the rainfall runoff actually decreases the pond's pH, which shifts the chemical equilibrium toward the non-toxic ammonium ion, potentially reducing acute fish mortality. So, to actually test these ideas, we have to isolate our variables. In a sudden summer hatchery mortality study, our independent variable, the thing we are actively manipulating, is the water temperature. Our dependent variables, the outcomes we measure in response, are the concentration of toxic unionized ammonia and the larval mortality rate. Now, to ensure our data is actually valid, we absolutely must lock in our controlled variables across all our test tanks. We're talking salinity, pH, dissolved oxygen, and stocking density. This systematic approach is what reveals the exact temperature threshold where harmless ammonia suddenly transforms into a toxic killer. Which brings us to Section 3, the quantum realm, atomic evolution, and electron rules. To really understand these chemical changes, we have to zoom all the way down to the fundamental building blocks of the universe. Our understanding of the atom has evolved dramatically over time. It's like a giant puzzle we've been piecing together. In 1803, Dalton thought atoms were just indivisible spheres. Then Thomson discovered the electron, and Rutherford found the dense, positive nucleus. By 1913, Bohr proposed that electrons move in fixed quantized orbits. But the real game-changer for modern chemistry came in 1926 with Schrödinger's quantum mechanical model. We finally realized electrons don't travel in simple solar system paths. Instead, they exist in orbitals, complex 3D mathematical wave functions representing regions of high probability. Now, in this 3D space, which is defined by distinct quantum numbers, electrons follow strict traffic laws. The off-bow principle tells us to always fill lower energy orbitals first. The Pauli exclusion principle limits each orbital to a maximum of 2 electrons, and they absolutely must have opposite spins. And then there's Hund's rule. This states that for orbitals of equal energy, like the 2p subshell, electrons will fill them singly with parallel spins before they ever pair up. Take the ground state of carbon, for instance. Because of Hund's rule, its outermost electrons occupy separate orbitals. That leaves unpaired electrons perfectly primed to form the versatile bonds that make all organic life possible. So, a crucial point in predicting how an element will behave is understanding its effective nuclear charge, or ZF. Think of this as the actual net positive pull from the nucleus that an outer valence electron feels. It's calculated by taking the total atomic number, Z, and subtracting S. S is the shielding effect caused by inner core electrons basically blocking that positive pull from reaching the outer shell, a concept governed by Slater's rules. Okay, let's look at one of my absolute favorite real-world examples of these quantum rules in action, copper. Based on everything we just talked about, you'd expect its electron configuration to end in 4s2, 3d9. But instead, it exhibits this totally anomalous configuration, 4s1, 3d10. It literally moves one electron to completely fill that 3D subshell. Why on earth would it do that? Because a fully filled D subshell offers a massive boost in energetic stability thanks to symmetrical charge distribution. And what's truly amazing here is that this specific stable configuration is exactly what allows copper to function as the essential trace element in hemocyanin, which is the molecule that transports oxygen in crustacean blood. And that leads us perfectly into Section 4. Periodic trends and marine toxicity, where we connect the micro right back to the macro. If you want a cheat sheet for predicting chemical behavior in the ocean, this is it. It all comes down to a few core periodic trends. As we move left to right across the period on the periodic table, atomic radius actually decreases because a higher effective nuclear charge pulls the electron cloud in tighter. Meanwhile, ionization energy and electronegativity increase. Conversely, as we move top to bottom down a group, the atomic radius increases as new electron shells get added, while ionization energy and electronegativity decrease. Understanding these directional vectors is absolutely everything. But before we apply those vectors to real-world problems, we need to talk about bioaccumulation. This is the gradual buildup of a toxic chemical or a heavy metal inside an aquatic organism over time, and it happens faster than the organism can metabolize or excrete it. Keep this concept in your back pocket, because those periodic trends we just looked at are the exact reason this dangerous phenomenon happens in the first place. Let's look at a case of biological identity theft via atomic radius. Cadmium is a highly toxic heavy metal contaminant, but because of its specific position on the periodic table, the cadmium ion has a radius of 95 picometers. That is dangerously close to the 99 picometer radius of calcium. To a crab's gills, they look nearly identical. So cadmium sneaks right into the calcium-binding transport proteins and competitively blocks the channels, utterly halting the crab's ability to biomineralize its shell. It's a molecular disguise. Which brings up a really vital question about organic pollutants. Why do organochlorine pesticides like DDT accumulate so heavily in the fat of apex predators like dolphins or tuna instead of just dissolving safely away in the vast ocean water? The answer lies in another periodic trend, electronegativity. The difference in electronegativity between the carbon and hydrogen atoms in DDT is less than 0.5 on the Pauling scale. This tiny difference creates completely nonpolar covalent bonds, and nonpolar compounds are highly hydrophobic. They absolutely hate water. Because they can't form hydrogen bonds with the ocean water, they partition directly into nonpolar environments. And in a marine ecosystem, the biggest nonpolar environment available is the lipid tissue, the fat of marine organisms. Finally, let's consider a classic science fiction question. Why is life as we know it carbon-based? Silicon is right below carbon in group 14 on the periodic table, meaning they share similar valence properties. So why isn't aquatic life built on silicon? Once again, it comes down to atomic radius. Carbon's smaller atomic radius allows its orbitals to get close enough to form strong, stable, side-by-side overlap, which creates strong pi bonds and versatile chains. Silicon is just too large. Its bigger, diffuse p orbitals result in weak overlap, making it far too unstable to serve as the molecular framework for life in water. So, we've traveled all the way from mandatory lab safety goggles down to the quantum wave functions that dictate whether a toxin destroys a marine food web. It all connects. I'll leave you with this final thought. If the shift of a single electron can collapse an entire food web, what other invisible aquatic mysteries are waiting for you to solve? Thank you so much for joining this explainer. Keep questioning the invisible world, and I'll catch you in the next one.